Awesome. Welcome everybody to Prompt Engineering for Vision Models with myself, Abby, and Caleb, my colleague from Comet. We recently released a short course with Deep Learning AI, so you can find that course on their website if you're interested. But in this workshop, we'll be doing a little bit of a deeper dive. We'll be going through some of the things we didn't quite have time to get through in the deep learning course. So just as a general overview of what we'll be going through in this course, you've probably heard of prompts for large language models and perhaps natural language processing, but prompts aren't limited to just text or just language models. Theoretically, any type of data can be a prompt. So text, images, audio, and video data. Ultimately, a prompt is just an input that guides the distribution of the output of a model. So, for example, in this course where we'll be working with vision models, visual inputs to diffusion models will be one example of a prompt. We'll also use natural language as a prompt to vision models for object detection as well as for stable diffusion. But we will get to that in just a moment. So overall, we're going to build a pipeline where we start with an image. We will give it a piece of natural text of something in the object to detect. So maybe an apple or a cat. And then we'll also give it a second piece of natural language text of what we want our model to replace that with. So say we have an image of a cat on the beach and we say, replace the cat with a dog. What this pipeline should be able to do is isolate just the cat in the image and replace it with a dog. To do that, we will be building a pipeline of multiple models. So we'll be going over image segmentation, object detection, a little bit about diffusion, and then finally in the last bit, we will also talk about how to fine-tune a diffusion model so that you can prompt the model to create images based on your own images. So say you wanted to replace that cat with your particular friend, Joe. You could do something like that. So let's get started. So first, we're going to work with image segmentation with the SAM model, also known as the Segment Anything model from Meta. And SAM is really interesting because it is in many places considered the first foundational model for computer vision. We've had quite a few foundational NLP models, but computer vision took much longer to develop a foundational model because of the way that emergent capabilities come out in computer vision models. So what we will do first is first we will pip install all of our packages. And we have Comet ML, Accelerate from Hugging Face, Diffusers, Transformers from Accelerate, and then Ultralytics will be using their implementation of SAM for this notebook. The reason we're using Ultralytics implementation is because it's much smaller. It's meant for mobile devices, so we can fit it into one notebook more easily. And then we'll import Comet. If you do not have a Comet account already, you can sign up for one for free at comet.com/signup. You'll need to grab your API key, which you can do by going to account settings and then API key. And then there's a few ways that you can set your API key. The easiest would just be to manually enter it in your init statement. If you don't enter it, it will just prompt you to enter it. So that also works. You can just initiate your experiment. And I think here it won't prompt me because I think it already has access to my key, but we'll see in just a second. And if you want to set it in your Google Colab secrets, that's the way I like to do it, because then I never have to think about it. Google just goes and fetches it from my secrets, and I don't have to think about it. Oh, there we go. So there, it's prompted us, and I'm just gonna go over to Comet and grab our API key. So once you get into your, yep, and then just paste it in. Awesome. So now we have our project instantiated, and now we're going to load the data that we need for this workshop into the environment. So we're going to do that by downloading an artifact from Comet. An artifact is basically any asset or file or folder structure that you want to upload to Comet Cloud, and then you can download it, or if you make it public, anybody else can download it too. If you have a team space or an organization and you upload an artifact to that organization's workspace, then anyone else can access it there. So I already created this artifact ahead of time. We also created a small GitHub repo with just some of the helper functions that we'll be using in this presentation. So we're going to clone that to our environment. So now we're going to start off with the image segmentation portion of this pipeline. And this is in the broader pipeline, this will actually be step 2 in the pipeline, but it's a little bit easier to explain what's going on here. So we're going to start with this and then work backwards again and then work forwards. So we import that utils file that we just downloaded from the GitHub repo. In that and in the artifact that we downloaded from Comet, we have a data file, and we have a number of different images that we'll use throughout this course. But first, we will use the dog's photo, as you can see here, and we'll just load that in, and we'll take a quick peek at it just to see what it is we'll be working with. And eventually, we will be segmenting parts of the image of these dogs. And we'll use different methods. So we'll use pixel coordinates, coordinate points. We'll also use bounding boxes. We can use natural language once we connect SAM with other models that can interpret natural language. And we'll also explore a little bit using multiple prompts, whether they're input points, bounding boxes, and then positive and negative prompts. So the next step, now that we have loaded our image, we need to resize it to fit our model's requirements. We'll just take a peek to make sure that it still looks the same. It's same proportions, just smaller. And now we'll import the model and prepare it for what we're going to do. Here you'll see that we are trying to connect to a GPU if that is available. If not, it will connect to your CPU. It's not really recommended that you use CPU for these notebooks because it'll take a long time, but you're welcome to try. So for our first example, we're going to use input points. So basically, in this first input point, you can see that we have the x coordinate is 350 and the y coordinate is 450. Just a note, in case you aren't familiar with the way the coordinates are on an image in Matplotlib, or it's the x is the lower axis, and then the y axis actually starts at 0 at the top and then maxes out down at the bottom, so that can be sometimes confusing. But you can see the green star right in the center is where our point is. So we just used our function from the utils file, show points on image, and we overlay that on top of our image. So that's the coordinate point that we're going to input into our model. Now we're going to pass that. We're going to pass the resized image with the coordinate point into our model, and we're asking it to segment the object that that point refers to. And the original SAM model actually returns multiple masks, 3, I believe, of the three highest likelihood, the 3 masks with the highly likelihood. So the 3 masks with the highest scores. So in that case, it could be perhaps for this picture, perhaps they return 1 mask with the entire dog with the jacket. Maybe they return 1 mask with the jacket. And you can choose from those. We've edited this to only return the mask with the highest probability. So it only returns 1 mask in this case. So now we are passing that information into the SAM model, and you can see that it did a really good job of segmenting the dog. One thing that I should mention is that SAM by itself, without any prompts, will just segment everything in a picture. So if you feed it a picture, it will segment literally every object. So it'll segment the dog and the background and the second dog and the jacket and whatnot. And you can set parameters that determine how many regions to break the image up into. To get just specific segmentation pieces, you have to input some sort of a prompt. So that's what we're doing here. If we didn't input any prompt, we would literally just get all of the segmentation masks back. So, so obviously that did a really good job, especially for a completely zero shot. We didn't train anything there. And above is an example of a semantic mask. So in segmentation, you have semantic masks and you have instant masks. Semantic masks mean, this above is an example of an instance segmentation mask. So an instance prompt will be a single example of a class. So here we have 2 different dogs, and when we input the prompt dog, it just we didn't use dog, we just used the point. If we had used natural language, it would segment each dog separately. So what we want is dog, and each dog is an instance of that class dog. For semantic segmentation, we would be selecting all instances within a class. So if we said dog, it would return a mask of anywhere in the image where dog was present. So it would return 1 image back with both of the dogs all segmented as 1 mask. So this is instance segmentation. And so that works really well, but what if the point that we put in the middle of the dog, we had actually intended to be for the dog's jacket, not for the dog itself? In that case, we can, so for this example, got a little ahead of myself. Moving backwards, say we wanted to do semantic segmentation, so we wanted both dogs segmented together. We could put in 2 positive prompts, as you can see here, and then we would hopefully get back a segmentation mask of both of the dogs all in 1 mask. This could be useful for an example like, say you had a picture with people in it, and to protect people's privacy, you wanted to blur every instance where there was a person just to protect their identity. That's a case where you might want semantic segmentation. So there we go, we have both dogs. Now back to the example I was just started to talk about. What if for that first point, instead of the whole dog, we had wanted just the jacket? So it had segmented more than what we had intended. In that case, we can use a positive and a negative point. So you can see the green star is a positive point and the red star is a negative point. We want just the jacket. We don't want the dog included. And let's see what happens when we feed that to Sam. It should be able to isolate just the jacket and not the dog. And again, there are different ways that we can prompt Sam, which we'll go through. So not just points. There you go. And it segmented just the jacket really well. So that's pretty incredible, I think. And it's super powerful, especially as we start to connect this model with other models in a pipeline. So now that we've done a positive and a negative prompt, we can also do, we can also prompt with bounding boxes. And with bounding boxes, we can also do positive and negative bounding boxes. We won't get into that here. It's pretty much the same concept as the positive and negative points. But instead of a single point, we can input the 4 points of a bounding box. So if this is our bounding box of this second dog, our hope would be that this second dog would be, it would return a segmentation mask of this second dog. Now, why this is really powerful, that we can use bounding boxes as input, is because now we can chain an object detection model to SAM in our pipeline. And now we don't just have the original SAM model, which segments everything in an image. Now we have a model pipeline that can detect an object and then automatically segment that object in an image. And that's what we'll be doing a little later on. But just to stick with this for a little bit, here we've defined our bounding box, and then in the next few cells, we will be passing the bounding box information to the model, and we will get the segmentation mask of the second dog back. You can see here that all of these masks are just binary masks or binary arrays of true and false. So, so these binary masks will be the same shape and size as the original image, with either zeros and ones. Zeros where the mask is not, one where the mask is, or false where the mask is not, true where the mask is, and that comprises the mask itself. And there's an example right there. So you can see it's all false because the outer bits of regions of the image are not where the dog is. So that's also worked really well using the bounding box. And we can take a look at just the binary mask itself. So I mentioned that it is a array of ones and zeros or trues and falses. When we print that array, we get this black and white image. Again, true or false, binary, black and white. So it's literally saying, just take this region where the white is, or the trues, and that is what we are referring to. Now, the binary masks are also interesting in that you can add and subtract them. You can perform different, obviously, different mathematical operations on them. Why would you want to do that? Say you had separate masks of the dog on the left and the dog on the right, and you wanted one with both. You could conceivably add those masks together because it's an array of zeros and ones to get the mask of both dogs together. You can subtract. You can also subtract masks. So say you have this mask of the dog, and you had another mask of the dog's face. You could subtract this mask. So subtract the mask of the dog's face from this mask, and you would hopefully get the dog's body back. So there's lots of fun things you can do with binary masks. But moving on to the next bit, now that we've gone over how to use bounding boxes with SAM, we're going to use OWLVIT as an object detection model. So OWLVIT is really cool because it's a zero-shot object detection model, meaning that you can prompt it with anything you want, not just text. It's not it doesn't give you a predefined list of categories that it has already been trained to detect. You can literally input anything you can think of. So like shoelace sneakers or, kitchen sink or whatever it may be. It doesn't have a predefined list of categories. So by creating a pipeline between OwlVit, and SAM, we'll be able to input conceivably any word that we can think of, and the output of that pipeline will be a segmentation of that object. So we could input eyeball, for example, and get a mask of the eyeball, or input dog and get a mask of the dog. So that's what we're going to do in this one. So again, we've loaded the same image, and just check to make sure that that is the same image. And this time, instead of using prompts or bounding boxes to generate segmentation masks, we'll just tell our pipeline what we want it to segment. And OwlVit is a model from Google. There's a few other models out there that can also do zero-shot object detection. Grounding Dino is one of them. So we have our image loaded. So now we'll use the OwlVit model. And first we'll import it from Hugging Face Transformers library. We'll specify the checkpoint, the specific version of the model that we want to use, base patch 32, and then we will load that version of the model into our notebook, which is all very easy thanks to Hugging Face. And now we will prompt it with text. So like we said, we want to just tell it that we would like it to segment a dog. We don't want to have to specify points or bounding boxes. And we'll pass the word dog to the pipeline. And you can see the output is a list of dictionaries. So a dictionary for each object that it detects, a label, dog, the bounding box coordinates, and at the beginning is the score. So the score will be the likelihood that the object it has detected is the object, the word that you have entered. It can be useful to use the score, for example, if you get a lot of results and you want to filter some of those out just by the highest scores, or perhaps you want to filter out by the lowest scores to see where a model is going wrong, and if you can figure out what reasons it might be going wrong. So we're going to take this information, the output from the output, the score boxes and labels, and we're going to pre-process them so that we can feed them into SAM, because SAM needs all of those inputs in a specific format. We're showing them on the image again, obviously. So here we can see it's very, very successfully detected both of the dogs, and it also displays its confidence score there. And so we take these bounding boxes, the bounding box coordinates. So again, we have that list of dictionaries. So we take those bounding box coordinates and we pass them to SAM, or in this case, mobile, the Ultralytics implementation of mobile SAM. What we also have to pass it labels. So so 1 is a positive label, 0 is a negative label. So obviously we want, for every instance of dog, the word prompt that we supplied, for every instance that it finds, we want it to return a list of positive labels in that same length. So that's what we did just there. And then we will isolate the masks, and then we will show them on the image. And so we'd hope in this situation that the pipeline would return one mask for each dog that it found in the image, and hopefully it will do just as good of a job as it did with the coordinate points and the bounding boxes that we manually defined earlier. So there we have, it looks like two masks. So each mask is in a different color. So a mask of the dog on the left and a mask of the dog on the right. And the only information that we input here was the word dog. So far now we have a pipeline with owl, VIT, and SAM, where we input a word, dog, and it outputs every, a segmentation mask for every instance of that word that it finds. So that's pretty cool. And just like we did before, you can do negative prompts with that pipeline, but we'll get into that again later. As I mentioned before, a use case for this could be, for example, to blur out people in an image to protect their privacy. So in this next example, we're going to use another image that is in that artifact we shared, that we downloaded above. And if you download that artifact, you will also have access to all of these images. It is a public artifact. So we're going to load the people.jpg picture into the notebook and take a quick peek at that. And in this example, we will be asking the model to detect every instance of a face, and then to segment just the pixels in that face, and then we're going to apply a blur filter to blur out just the faces. So, but before we do that, we do have to resize the image so that it is correctly formatted for input into LVIT, just like we did above with the dogs. And then you can see here the image. We have 5 happy people. So great image, but we want to blur all these happy faces out to protect their identities. Great, so now, and we can just do a quick double check raw image.size to make sure that we have the required input size, which is 600 by 400. Always good to double check that. So now that we have our input image in the right size, we are going to define what it is we're looking for, what we want LVIT to look for. So above we specify dog. Here now we'll specify human face. Interesting fun fact, when I first made this notebook, I didn't say human face because that is a little bit of an awkward phrase, I think. I just put face, and it was not able to detect all the faces. So a great lesson for any prompt engineer in the making. Sometimes the first prompt you give will not yield good results, and sometimes you'll have to play around with the prompt quite a bit till you find something that the model understands. And sometimes that doesn't feel very natural. But anyways, this is tangent. So we've asked it to detect all the faces, and it will return the owl VIT will return the bounding boxes of those faces. Then we'll pass the bounding boxes into SAM, and SAM will create the segmentation masks. As you can see in here, we also did experiment.log image. That is we created a Comet experiment. So we are logging each of the images, or an image at each step along the way, so that we can track how our model is doing. This can be super helpful if, for example, you get an output image that that is incorrect. You know, maybe it only output 3 of the faces, or maybe it output something other than faces. By logging an image at each step of the way, you can then go back and figure out, oh, okay, it was something with the SAM model. That's where I need to fix it. Or as in the case with the phrase face, I was able to immediately see that it was not able to detect the word face. So I knew that it was something about the OWL VIT model and that I needed to change up my phrasing. So that can be super helpful. Anyway, so now we're feeding these bounding box coordinates into SAM. And in order to blur the faces, first we have to create a copy of the image and blur the entire image, just like this. And then we'll use the masks of the image to isolate just the areas of the image that are where the faces are. And so we use numpy.where, and we specify that anywhere where the segmentation masks of the faces are, we want to show the blurred image, and anywhere where the segmentation masks are not, we want to show the original image. So that's what we have here, and it's actually a pretty cool result. It even detected the sunglasses for the guy on the left and decided not to blur the sunglasses, which was a surprise to me. I thought that was pretty interesting. But this is an example of something that you can do once you build that pipeline between an object detection model like OWL VIT and a segmentation model like SAM. You can start doing lots of other fun things like applying a blur filter or any other filter. In the next example, we will use the same pipeline, but instead of just blurring the regions that were the faces, blurring the regions that were detected by the segmentation model, we will actually be replacing those regions with all new generated images via the stable diffusion in-painting pipeline. So now we will have the OWL VIT object detection model as the first step. The second step will be the segment anything model for the segmentation. And then as a third step in our pipeline, we will connect the stable diffusion in-painting model in each of those steps. So we'll put the input to the OWL VIT object detection model will be a text of what we want it to isolate. And the output will then become of the OWL VIT model will then become the input to the segment anything model. The output of the segment anything model will then become the input to the stable diffusion model. And ultimately, the output will be our image transformed as we want to transform it. So now we are looking at a obviously different picture. It's a picture of a little boy with a cat. So as mentioned, in this case, we want to input a word of what we want the object to detect, and then replace it with entirely new generated image. So we have detected the mask of the cat, and that looks pretty good. And we are going to instantiate the stable diffusion pipeline, again from Hugging Face. Here you can see that we are checking to see if we're on a GPU or CPU and adjusting certain requirements accordingly. Low CPU memory usage, for example, or whether the data type we use, whether it's a Torch Float 16 or Torch B Float 16. Great. So now first we'll set the random seed, and we do that so that we can have reproducible results. And we will set that seed into the torch generator. Our prompt for the stable diffusion model is going to be a realistic green dragon. So we've prompted the OWL VIT model to detect the cat, and we've prompted the stable diffusion model to replace with a realistic green dragon. And now we will instantiate a Comet experiment and run our pipeline. And we should get back or return not the original image with the cat, but the original image with the cat replaced as a green dragon. So if we want to look at the image that we just logged to Comet, we can click on the URL there. It will link directly to the experiment you just ran. And once we're in the Comet UI, we can just navigate over to the graphics tab on the left. We can take a peek at that. And you can see that's a dragon. It's, you know, maybe not the prettiest dragon in the world, but we, as you can see in the image metadata that we logged, we only did 3 inference steps. That's not very many. That's partially to save time and space. So if we wanted to improve, there's a lot of things that we could do to improve the quality of this dragon. It's definitely there. You can see definitely the outline of a dragon. And in order to improve the dragon, there's a bunch of different things we can do, like increase the number of inference steps, which we'll go over. We could also play around with the random seed and see if a different seed gave better results. But for our tutorial, we're going to keep the seed the same, just for to keep our experiment scientific. And we will play with number of inference steps. We'll also play with a couple of other hyperparameters like guidance scale and strength. But first, as mentioned, 3 inference steps isn't very much. It's pretty understandable that we didn't get a very detailed image. For some context, diffusion starts with random noise and slowly subtracts its prediction of what is random noise. So the fewer inference steps you have, the more your image will look like just random colors. And then the more inference steps you have, it will slowly get better over time and look more realistic to a point. At a certain point, it doesn't really help to increase your inference steps anymore. At a certain point, the model does as well as it can. I think for this particular version of the stable diffusion in painting pipeline, the recommended number of inference steps is not over like 75. As in, you can increase the inference steps past that, and you're not at that point, you're not going to see much of the difference. So we're opening our Comet experiment. We can go to our graphics, and this is with 100 inference steps, and that doesn't look very good, but yeah, that's not very good. Well, then it's definitely something we need to keep playing with. Try to tune. If we go back over to the notebook, I'm wondering, did we change any other hyperparameters in that, or did we just change the number of inference steps? Interesting. Okay. So that wasn't what I would have expected by any means. I would have expected it to get a lot better at 100 inference steps. But given that it didn't, there are a few things that could be going wrong here. Caleb, do you have any idea?
Yeah, so very often when you have too few inference steps, you'll see an image like this where you have these sort of digital, noisy, almost chrome-like aspects to it, which is just the image being very close to pure noise. When you overshoot the number of inference steps, not only does you start to get diminishing returns, it can actually sometimes start to delete the image, or you get this kind of effect where the background colors look really nice. Actually, they kind of correspond to the original image, and everything. If you were to isolate any detail of this, it would sort of be plausible as part of the broader image, but it no longer looks like the thing you're trying to generate. And so there's a sweet spot that requires some iteration. It varies depending on the version of Stable Diffusion you're using and the image you're trying to generate. In this case, we would likely try something like 50 and see where that got us.
Thank you. Super helpful. So, awesome. And then, So obviously 100 inference steps was too many. So let's set it back down to 50 like Caleb just did. And then now we'll talk about guidance scale. And I think, Caleb, you have some really good information on guidance scale, don't you?
Yeah, the guidance scale you can think of basically as a scaling factor that tells the model how much to care about your input, how much to care about the thing you're asking it to ask. Sorry, sometimes speaking is very hard. It tells the model how much it should care about the prompt you're giving it. So if you set your guidance scale to 0, the model might just ignore the prompt you've given it and generate whatever it wants. If you set the guidance scale very high, the model will generate with a high fidelity towards what you prompted it, but oftentimes it will be less creative and less high quality in many situations. So as with inference steps, there's typically a sweet spot that's going to vary a little bit. One thing to note about guidance scale and some of the other hyperparameters we'll be looking at is that the range of values that they take on, or the default values, varies quite a bit between diffusion models. Whereas inference steps is a sort of atomic value that is the same. One inference step is one step of inference, no matter what model you're using. 1 point in guidance scale can be very different depending on which diffusion model you're using. So you want to be sure you're checking the model card if you're using Hugging Face, or just the metadata available for your model.
Awesome. Great. So as Caleb mentioned, the lower the guidance scale, the less sort of strictly the model will adhere to whatever your prompt is. And the higher it is, the more strictly it will adhere to your prompt. But on both ends of the spectrum, it can be at the cost of creativity. So you'll probably get more creative outputs with a lower guidance scale, but less creative with a higher guidance scale. And again, here we have logged that image to Comet. What can be really helpful, for example, is if you are trying out a bunch of different guidance scale values, maybe you're doing a sweep, to log each image, to create a list of guidance scale values, for example, and log each image that's created with each of those guidance scale values. And if you log them to Comet, you can then go in and you can examine each of those images and compare them against each other side by side, and determine your best guidance scale value that way. Otherwise, it can be a little bit difficult to compare, to store all of your output images in one spot and compare them. It can definitely be tricky when, even once you have a pipeline set up and you're trying to figure out the right sets of hyperparameters for a given image, because you'll often want different hyperparameters for different images. It can be helpful a lot of times to work backwards. So to go into your project, go into your graphics, look at all your output images, and then pick the best one and work backwards and figure out what were the hyperparameters that I used to create this output image, rather than the other way around.
So we can see here several different images generated with different guidance scale values. This one is at 1.5. Got a little bit of the cat. We got a little bit of the dragon coming in here. Still left coming in, but there's still some cat left. At 2, there's less cat. You can see a little more dragon coming. Over here at 0.5, it still looks like a cat. There's very little dragon coming through. So you can see as the guidance scale goes up, the dragon increases as well. So we can even try running increasing the guidance scale more, logging it to the same experiment. Sorry, a new experiment to the end of this experiment. And let's try adding.
Why don't we try like around 7.5, I think is usually the ideal guidance scale value.
Yeah, let's try 7.5. Let's see what happens. And as you can see, we start to get some dragon features in. We're not where we want to be yet, but we're starting to see a little more progress. There's less cat in this image, more dragon.
And then the last hyperparameter we'll be discussing is strength. So strength describes the amount of the original image to the amount. So this is for in painting specifically, not necessarily for diffusion, but how much of the original image to leave in the new image, and how much of the for the area where the image generation is being applied, how much of that should be the new image and how much of that should be the old image. So a lower number will make it less, I guess, new and different. So you'll see, for example, more remnants of cat in a lower strength value. And then a higher one will sort of disregard the background image completely and just create whatever you've prompted it to create.
One way I like to think about strength is in the diffusion process when we're adding noise to an image, specifically when we're doing in painting, or that is when we're editing out a portion of an image. The noise adding process is sort of like erasing the part of the image we want to replace. And the more strength we add, the stronger that noise is, and so the more we erase of the original image. So if the noise is, if the strength is really low, in this image, for example, we'll erase very little of the cat. And a lot of that will still be incorporated in the final image. Whereas if the strength is extremely high, we'll blow away the entire background within that segmentation mask. And so we'll generate a cat, or sorry, we'll generate a dragon, but it might not have any context for the background image, and it might look sort of out of place. So we want to find a nice balance where it generates the image we want, but it incorporates some of the contextual details around it to make something that blends into its background. You should also note that the stable diffusion pipelines do an automatic adjustment of the number of inference steps based on the strength. This is because if you're adding more noise, you'll need more inference steps to remove all of that. And if you're adding less noise, you'll likely need fewer inference steps. So you can do it with or without this calculation, but it's a nice feature of Hugging Face's pipelines. Here you can see here you can see an image generated with 200 inference steps and a strength of 0.3. Still see the shape of the cat here. Some of the more dragon-esque looking ones, this is starting to head in the dragon direction. You can see this has a strength of 0.5 with, as you can see, like there's some nice, it still looks very cat-like, but you see the dragon scales and skin, but it's still blending into its background fairly well. Here's an image with the strength turned up more, and you see there's less cat in this image. And here's very high strength, where it's blowing away a lot of the underlying image. Sorry for interrupting, Abby.
Oh no, and then that is all for the pipeline that we're going to create. So we wanted to create a pipeline where we prompted our pipeline with text of what we wanted it to find in an image, and then we wanted to prompt it with what we wanted it to replace in that region of the image. So in this last example, we prompted it with the prompts cat, firstly, and then a realistic green dragon, and we wanted it to automatically detect where the cat was and replace it with a dragon, and we successfully did that by building a pipeline with all of the EIT from Google, the segment anything model from Meta. Here we used the mobile version from Ultralytics, as well as a stable diffusion in-painting pipeline from Hugging Face. And yeah, that's our successful pipeline. For the next bit, Caleb's going to show us how to fine-tune a diffusion model so that we can create images based on our own personal images. So say you wanted, instead of replacing with a realistic green dragon, for example, you wanted to replace with your sister or your own dog or cat. You could train this diffusion model on pictures of your own dog or cat using a method called Dream Booth. And take it away, Caleb.
Thanks, Abby. Yeah, so everything we've done so far has been focused on using diffusion models and segmentation models and other vision models to edit images based on information that's already in the models. So for instance, we're using diffusion models to generate images that they've already been trained on. A natural question is, how do you get a diffusion model to generate a concept it's never seen before? Fine-tuning in a traditional sense can be really expensive with diffusion models, especially as they get larger. And so in this section, I want to look at a technique that is a lot more resource efficient and will allow us to fine-tune a model to generate images of a particular person, for example, using only a data set of like 12 images of the, or sorry, a data set of 6 images of them, and very little compute resources, relatively speaking. Here, in this project, we're going to be tuning a model to generate images of our good friend Andrew Ng. And here you can see what some of these outputs are going to look like by the end. Here is Andrew and a Picasso. Sorry, not Picasso. Here's Andrew and a Van Gogh. Here's Andrew as Santa Claus. Here's Andrew posing as the President of the United States with a dog. Yeah, so let's dive in. The technique we're going to be using is called Dream Booth. And before we get too into that, we'll go ahead and install our dependencies and clone in our code. As well as initialize Comet and our model, or set our model name, sorry. And while all of that is running and installing, we'll talk a little bit about what Dream Booth is. So Dream Booth is a technique that was released from the Google research team. It is focused on tuning models in a really resource efficient way. And it does that by making use of what we call the model's semantic prior knowledge. In other words, if we want to tune the model to generate images of Andrew, well, the model probably has a pretty good understanding of what a man already looks like, right? And so we can leverage that, that previous understanding and give it very few images of Andrew and ask it to identify the specific differences between a sort of generic man and its understanding and Andrew, and begin to identify Andrew with these really particular traits. This is sort of how you might learn a new word based on context clues while you're reading. This is an image from the Google Dream Booth paper, and it shows how they took the input images of this puppy, and they put it in the Acropolis, or in a doghouse, or in a bucket, or sleeping, or swimming, and after limited training, the model was able to generate the dog in all these different contexts really successfully. Dream Booth belongs to a sort of category of training techniques that you might be familiar with if you've played around with the fusion models, that work by targeting or by retraining the model to update its understanding of tokens that are very rarely used. So, for example, if we were to train Dream Booth, if we were to use Dream Booth to tune Stable Diffusion to associate the word man with Andrew specifically, we might mess up our models we might trigger some sort of drift in our model, such that it now thinks that all men in the world look like Andrew. And while that would be a better world, it's not ultimately what we want here. So what we want to do is pair the word man with a token that the model rarely uses, like this brackets V character here. We want to combine the brackets V token with the token man to create a pair that the model can start associating specifically with Andrew. It's going to leverage its understanding of the word man, which we'll call the class, with its new learned understanding of the modifier brackets V. Fundamental in this concept, in this technique, is this concept of what we call prior preservation loss. And this is a custom loss function where we take images of Andrew and we give them labels, like a prompt of a brackets V man. We call this the instance prompt, and this is the instance data. We also take images of, we also generate images with our model using a prompt that does not have our target token in it. So instead of a photo of a brackets V man, we generate a photo of a man, right? And it's important that we sample these from the model. These aren't just taken from the internet. We call these the class prompts and the class images. And the reason it's important that we take them from the model is because we're going to use these during the training loop to make sure the model doesn't drift far away from its previous understanding of all these concepts. So to illustrate this a little more precisely, each step in the training loop, the model is going to make two predictions at least. One, given a prompt like a photo of a brackets V man, and another given a prompt like a photo of a man. It's going to compare how well it generated an image from the instance prompt against our image of Andrew. And it's going to compare how well it generated an image of the class prompt given an image that it previously generated. In other words, if during the training, it starts generating different images for the same prompts, we want to penalize that to keep it from drifting away from its previous understanding of a photo of a man. Ideally, this means that the only path the model has to learning what Andrew looks like is by modifying its understanding of the brackets V token. So with all of that preamble out of the way, we can get into writing some actual code here. We've abstracted a lot of the underlying stuff away, not because it's not interesting, and you can look at all of it in the source code for this, but just for the sake of speed and making it easier to read, we've created some utility classes. So let's start by isolating our token that we want to modify. That's this brackets V here. Isolating the class that we want to target, that's the word man, and then creating our prompts. We have an instance prompt, which is a photo of a brackets V man, and a class prompt, which is a photo of a target class, which is the word man. We're also going to set some hyperparameters for our training run. We're going to manually set a seed, which will make it easier for us to reproduce our experiment later. We'll specify the pre-trained model we want to use, as well as the variance, the resolution we want to generate at, the number of inference steps we're going to use, the guidance scale. We'll set the number of class images we want to generate to create our class data set that we'll sample from. We'll set that at 200. 200 is a pretty good number. It can vary a little bit depending on which model you're using, but in most cases, 200 will work. We'll also set the prior loss weight, which is how much we're going to scale the penalty for drifting away from its prior understanding of the class. If you set this really low, the model might train faster to learn a representation of Andrew, but it'll probably damage its other understandings of words like photo or man. If you set this really high, it might train a little slower, but it's very unlikely that you'll drift. And then we'll set our batch sizes. All of that out of the way. So once we've initialized our hyperparameters, we can start a Comet experiment. And then we'll import one of the utility classes we've defined. This is we're calling this Dream Booth Trainer. And this is going to have a lot of the methods we use throughout this course. So for instance, it has this generate class images method, which we would use typically to generate the 200 class images we're going to sample from. Now, even on GPUs, that will take a chunk of time. So instead of running that here, I have previously run that with using these same hyperparameters and save the output as a Comet artifact. So we can just download the class images directly from Comet. If you're curious ever about looking at the source code of any of these functions, you can always use the double quotation mark operator, which in a notebook setting will display the source code. And it will let you see exactly how messy my code is when I'm not running in a notebook. Now that we have that initialized, well, let's go ahead and download that class. Let's go ahead and download those class images via Comet artifacts. Because this is a data set, Comet's going to download it as a zip file, which we will then unpack. And we'll use the display images function on our trainer class. We just pass in the name of the folder where our images are at, and it'll display them in a grid like this. And so we can see, even though this is an older version of Stable Diffusion, this is 1.5, it still generates very good images, and it runs pretty efficiently on our resources. So we're off to a good start. Let's go ahead and download our data set of images of Andrew as well. This is also stored as a Comet artifact, and we can display it as well using the display images function. As you can see, Andrew owns a lot of blue shirts. Also, we have a data set that is harvested from the wild. So they're different sizes. They have different kinds of backgrounds. Andrew is shown at different distances, and all of that is totally fine using this technique. Okay, so we're going to get into the training in a second. Before we do that, we want to get our models ready to train. So we're going to use this initialize model function, which will extract a tokenizer, the text encoder model, the variational autoencoder, the UNet model, and that's it. All right, let's get started. Now, before we actually start training, we should introduce the technique we're going to be using. Besides Dream Booth, we are also going to use a technique to speed up the training process. In particular, we're going to use LoRa. Now, many of you are probably already familiar with LoRa and the family of training techniques it belongs to. But in case you're not, LoRa stands for low rank adaptation, and it is one of many techniques for efficient model training or fine tuning that takes advantage of the fact that the weights of a neural network are oftentimes low rank. That means that we can decompose the weight matrix into smaller, lower rank matrices, which we can then train instead of the original weights. In other words, in traditional fine tuning, we might update this underlying weight matrix, which we can call W, and that may be really expensive because the weight matrix is huge. But if we could decompose it into two significantly smaller matrices, we'll call them A and B, we could train those instead of W. And that would be a lot easier on our resources. We could do it a lot faster, and the resulting files would be much easier to store. So as you can see, this training, you can see the difference between a normal training update here, or quote unquote normal, and a LoRa training update, which is that our underlying weight matrix doesn't really change in the LoRa training paradigm. We sometimes call these matrices, these A and B matrices, adapters, because you're ultimately training them separately and then adding them into your base model. And so we could train several sets of adapters for different concepts we want the model to generate, and then load them in fairly quickly using the same base model, swapping them in and out. This is you'll see this sort of category of technique applied a lot. Things like LoRa or QLoRa or Galore, but they all kind of exploit the same basic idea. All right, with all of that rambling out of the way, we can get into training some actual models. The first thing we want to do is initialize a scheduler. This is our noise scheduler. Throughout the diffusion process, when we're training, we want to add noise to our images, and the noise scheduler gives us a more dynamic way of doing that. We want to use this initialize LoRa function to get our unit prepared for LoRa fine-tuning. We want to do a bunch of setup work to extract our optimizer and our data set, and our data loader, and our learning rate scheduler, and that kind of stuff. And we've created utility classes for all of that here. And then we want to send, we're using Accelerator, we want to send all of our models and our data sets and stuff to the correct devices. So we use trainer.accelerator.prepare. And this .accelerator is just an accelerator initialized under Hugging Face's accelerator. We just attached it to this trainer class for convenience. And now we can get into actual training. So one of the first things we want to do is set up a global step and an epoch variable, which we'll use for tracking, and create a progress bar, because I just like the way a progress bar looks. And then we can get into the actual training loop itself. We're going to iterate across every epoch, every step, standard training stuff. For each batch, we're going to extract the pixel values from our images. We're going to pass them into our variational autoencoder, which is the first step, which is one of the early steps in the diffusion process, to get them into the to convert our image from the pixel space to the latent space. We'll then generate a vector of random noise, which looks like our model's input. And from that, we'll generate our time steps, which we're going to use to select where we insert our noise. Here, we take the step of actually adding noise to our model input at different time steps using the noise scheduler. This is what you might see in the literature as the forward diffusion process, where instead of denoising, we are noising our image. Next, we want to extract the prompt we passed in. This is the text embedding of the prompt we passed in. We call it the encoder hidden states, is what you'll see it referred to a lot in the literature. But it's really just the embedding of the text prompt we passed in, which we'll use to condition our diffusion process. So it will give it the model an idea of what it should be aiming for as it starts removing noise. We pass all of that in to our unit function, our unit model, to get our actual prediction. And then we set our target. The target of the diffusion process is to isolate the random noise, and then ultimately isolate the random noise in the image. So we'll set our target to noise. Because we're passing in an instance, a piece of instance data and class data, and we're stacking them on top of each other, we can separate the two using torch.chunk. So here we get the prediction that our model made for the instance data. That would be a photo of a brackets V man, and the prediction it made for the class data, which would just be a prompt like a photo of a man. And then here are the two targets. Same thing. This is the target for the instance, and this is the target for the class. We'll compute just the mean standard error loss for both the instance and the prior or the class. And then we'll add them together, multiplying the prior loss by the prior loss weight that we defined earlier. And this is right here. This is the class prior preservation loss that we've talked about so far. Once that's all the way, we do the normal training stuff. We backpropagate the loss. We step our optimizers and our schedulers. We zero out our gradient, and we increment our global step. We're also going to log, capture all of our loss metrics and log them to Comet along with our step. You can log a bunch of metrics all at once to Comet as a dictionary like this and give it a step or an epoch for charting. And then we'll update our progress bar. We'll exit out of the training loop if we've exceeded the maximum of training steps we want to run. And when it's all done, we'll save our weights. We'll add a tag to our experiment so that we know this is a Dream Booth training experiment. And we'll log our hyperparameters. Comet does treat hyperparameters differently than other data, and you can log a dictionary containing your hyperparameters. For some libraries, it'll automatically track them, but in general, this is the format. So we'll run that, and we're only going to run this for 1 or 2 steps before I pause it, because even on GPUs, this will take a little bit of time. But we just want to see that this code actually runs, and yeah, there it is. You can see we're on step 1 with apparently 35 hours left of training. Oh, 15 hours left of training time. So our luck's improving every second, but out of mercy for everyone else. We'll pause it there. And similar to before, I ran this code previously and logged the results to a Comet experiment, and we can just reinitialize that experiment and view it here. So this is the experiment key from that previous experiment. And if I call experiment.display, you can see the actual Comet UI. And this is really nice for when you're within a notebook setting, but of course we can also just go to the Comet app itself and view this experiment. So this is the default dashboard that I've created for this project. In these charts, we're logging specifically this zany fascia experiment. But you can see the instance loss versus the step. You can see, oh, sorry. Did not mean to hit edit there. Pull that back. Yeah, you can see the instance loss versus the step. You can see the prior loss versus the step. And you can see the overall loss versus step. Now, when you're looking at this, it might seem like the model's not improving, like it's not approaching any sort of convergence. It's so spiky. And this is something that's really important, and it's a focus of this course, which is that with the diffusion models, you have to be visually inspecting the outputs to get a sense of how the model's performing. So we'll get into this a little bit later, but to give you a sneak peek, here's a panel I created to visualize the outputs of this model. And you can see that the model is, in fact, learning how to generate images of Andrew. But it's not really showing up here, right? That's okay. Again, we want to be visually inspecting it and seeing that the training process is working, even if we're not capturing it perfectly in this function. There's also other interesting things we can see here, like at different points, and because the prior loss and instance loss charts are perfectly aligned in terms of their axes, it's really easy to compare how they changed in unison. And so sometimes they rise and fall together, but there are lots of times, like here at step 99, where we see an improvement in one, or in this case, yeah, at step 99, we see the instance loss begin to spike upwards. Whereas at step 99 in the prior loss, we're still going downwards, right? And there's a lot of these kind of seesawing moments throughout the training run. And it's interesting to think about what might be going on there. Maybe what's happening is that the internals of the model are shifting around, and so the loss might not seem to be improving, but it's actually arriving at a better representation of what Andrew is without damaging its prior knowledge. And somehow in this seesaw back and forth, even though the loss metric isn't changing, it's finding better aligned weights. In any event, we want to verify this. We clicked on the wrong notebook. In any event, we want to verify that this is actually happening. So let's run a quick validation loop. Here I've created a series of prompts, some targeting the brackets v man token pair, and some equivalent but not targeting the brackets v token. So you have the instance prompt here, a photo of a man, a photo of a brackets V man riding a horse, and the class prompt, a photo of a man riding a horse, right? And what we'll do is we'll pass both of these into Stable Diffusion. We'll generate some images, and we'll compare their outputs to see how they do. Now, the training code here is pretty straightforward. This is actually a larger version of Stable Diffusion, but we're not going to run this inference code. So I said training code previously. I meant inference code. We're not going to run this because it'll take a while. But this is just to show you what this code looks like. You would just switch this out for the 1.5, which we used before. Both of which are available as artifacts on Comet if you want to play with them. We previously ran this code and logged it to an experiment here, which we can run. And if you display that experiment in the UI, you'll see the project that we were just viewing. And you'll see that it logged it all to this panel. A panel in Comet parlance is a custom visualization. This particular panel is actually a Python panel. So the code that generates this visualization is not some sort of domain-specific language. It's not built in a UI. This is just a Python function like you might run within a Jupyter Notebook cell, and it's run on a different server, and its output is generated into our dashboard. So we can click back over to the project. We can view these images directly. And as you can see here, we have pairs of images like a mural of a brackets V man painted by a graffiti artist. You get this kind of Banksy-esque mural versus this image, a mural of a man painted by a graffiti artist, where you end up with someone who doesn't look anything like Andrew. Or a photo of a brackets V man playing basketball. You get a man who looks vaguely like Andrew playing basketball versus a photo of a man playing basketball who looks nothing like him. There's other interesting things too, like because we've only ever shown the model images of Andrew facing head on to the camera, whenever we add the brackets V man pair, the image always has a person facing forward. When we don't add that, it's like in this photo, a photo of a man riding a horse, we often get a man looking away. So there's little aspects like that you need to be aware of in your data set as you're tuning, because some of there can be unintended consequences for what the model actually learns. But in general, this is a good way to make sure your model is actually learning and to inspect the output side by side. We can go into the Comet graphics tab for this particular experiment and get a larger view of each of these images as well. So here we go again, a photo of a man playing basketball against a photo of Andrew playing basketball. This doesn't look perfectly like Andrew, but we're trending in the direction. Other images are even better. This is just a photo of a brackets V man. This obviously is Andrew. Or the mural image, which we spoke about earlier. Again, very high quality image of Andrew. And that concludes our lesson on fine-tuning with Dream Booth. There's a ton more you can explore here. There are various versions of Stable Diffusion which you can use. You could experiment with different prompts for your images. And in this situation, we use the same class prompt for every single one of our class images and the same instance prompt for every single one of our images of Andrew. But some people even use models like Blimp from Salesforce to generate custom captions for all of their instance images. So we might end up with a bunch of images with captions like a photo of a bracket V man speaking on a stage, or a photo of a brackets V man taking a headshot, whatever. Whatever we have in our data set. In terms of next steps, though, you're all invited to download these artifacts from Comet to play with these data sets and these models yourself and to log your experiments, and we hope you do.
Woo!